Okay, in this problem we're asked to calculate the force that's exerted by a long current carrying wire on a wire segment. Now this is a little bit different than the problems that we've usually been doing in class, and the B field in this case is not constant. The magnitude actually changes over the wire segment I2, so we're going to have to break up I2 and integrate. So in order to start the problem, let's figure out what the magnetic field is at the location of I2. So here's my long wire I1, and I draw a dotted line which shows me where I2 is. What's the B field along this particular direction? Well, we know that the magnetic field from a wire is given by mu naught I1 is the current in this case over 2 pi r. So the B field falls off as you go away from the wire with a value of 1 over r at distance. So that tells us the magnitude of the B field. What's the direction of the B field? Well, I can use the right hand rule, and you can't see this, but I can put my thumb along the direction of I1, my right thumb, and I can curl my fingers around in order to figure out which way the B field's curling around. And if I do that, I can see that at the plane where the wire is located, the B field is actually pointing into the page. Okay, so I know the B field at the location of this wire segment is mu naught I1 over 2 pi r, and it points into the page. So now let's figure out what the total field that's exerted on the wire segment is with this information. So now I'm going to draw I2 going down like this. I know the B is into the page. And what I want to do is I want to figure out the force on a little segment dl. Okay, well, I know that the force on a wire segment is equal to the current times dl crossed with the B field. In this particular case, then, the magnitude of the force is going to be equal to I2, the current that's flowing through the wire segment, times dl crossed with the B, which is just going to be equal to B. And the reason is that the B, since it's into the page, is 9 degrees different from dl. What's the magnitude of dl cross B? dl sine theta is actually just equal to dlb. Now, since I'm moving in the r direction as I've defined things, I'm moving outward from the wire, I'm going to make the identification that dl is equal to r. That is, I'm going outward in the r direction. That allows me to write the differential field, df, is equal to I2 times dr times the B field, which we already said was mu naught I1 over 2 pi r. Okay, so now we're in a position to calculate what the total force is in this case, just by integrating. So I'm going to write my expression, I1, I2, mu naught over 2 pi. All those are constant, dr over r. For my limits of integration, I'll go back to the problem specification. I start a distance of d away, and then I go a total length of L. So if I ask what happens to R as I integrate, I start at R is equal to D, and I end at R is equal to D plus L. So that establishes my limits of integration. Since I'm integrating over R, it's important that I start consistently at the right R value. And since, again, looking at the picture, the initial value of R is D, and I end at that R value, D plus L. Okay, so I have an integral here. Rewrite the constants, mu naught I1, I2 over 2 pi. Now the integral of dr over r is pretty straightforward. It's just the natural log of r. And this is now from d plus L to d. Okay, so now we can figure out what the net force is. Just mu naught I1, I2 over 2 pi. It'll be natural log of d plus L over natural log of, or minus natural log of d, and just using the relationship between log A plus log B is equal to log AB, I can write down the force like this. Oops, box around it. Okay, so there's the magnitude of the force that's exerted on the wire segment by the long wire segment. You can also ask which way things point. Again, you can't see this. I come up my fingers along I2, and I can curl in the direction of B into the page. I see that the force actually points to the right.